Okay, so I'm happy to welcome today for the first of 3 academic training lectures Christophe Grojean from DESY and University of Humboldt University Berlin. Christophe has done his PhD in the 1990s in Saclay, and he has always worked at the interface between what we know about the standard model and what we want to know about the standard model and beyond. So beyond the standard model physics. He has done so first with a PhD in Saclay, then going to Berkeley for a postdoc, then returned to Saclay, then as a junior staff here at CERN, then to Barcelona for a faculty position, and now he is since already 8 or 10 years in Germany for a faculty position. So his trajectory and his physics focus shows he is a true European, standing up since long for a truly European and worldwide project, namely the FCC, where he has been involved, I think, since the beginning in making the physics case for the FCC. And we are very happy to have him here now for 3 lectures on the physics of the FCC. I should say on Thursday evening at 6 p.m. there is an alumni talk also about Future Collider by Carl Jacobs, for those who are interested. I should also say this. These lectures are recorded. The question and answer sessions are not recorded. So at the end of the section, we go to questions and answers. We have by now, I think, almost 100 or 75 people online. If they want to raise questions, they can do so at the end, or they can write in the chat and I present the questions. So without further ado, Christophe, please start. Thank you for having you here.
Okay. Thanks a lot. So it's my real pleasure to be here today to introduce the motivation, the physics motivation for this big project that hopefully take place at CERN with the first collision in something like 20 years from now, right? So maybe we should all come back in 20 years and celebrate the first beam collision, right? So as Urs said, there will be 3 lectures. So the first one will be a general introduction about the physics motivation, and I will also describe a little bit this feasibility study report that came out earlier this year, right? Okay, so first of all, I want to thank really the FCC feasibility study team that has produced this 3 volume. It's about 1,200 pages that you can read at night before going to sleep. And I will really focus today on the first volume, which is dedicated to the physics, but you can also enjoy the volume 2 about accelerator and technical infrastructure, and the volume 3 about civil engineering and the implementation, the territorial implementation near CERN, right? So to really appreciate the physics case of FCC, you first need to really understand what is the situation of particle physics after something like 13 years of LHC running, right? So you all know that the major discovery of LHC has been the Higgs boson that came up in 2012. But there is also another important discovery, is that actually the LHC hasn't discovered any other new physics, right? So here I say that LHC is Higgs plus nothing. Of course, I put a big asterisk in nothing, because nothing is really from the point of view of physics beyond the standard model. But if you're interested in the standard model, actually the LHC has been a great success, right? A lot of progress in our understanding of the standard model have been improved measurement of all the standard model processes, precise measurement in flavor physics. Let's see if I can manage and also new frontiers in heavy ion studies, right? So really, thanks to the firm experimental control of both experimental and theoretical systematic uncertainty, actually the LHC really became a precision machine. It was not really designed to do precision measurement. It was there to actually discover new physics, but actually it turned out that it has been really a successful measurement machine, right? So this simple equation, right, that the LHC didn't find anything else, means that we need now a new machine which will provide more energy and more precision to really push the frontier of knowledge and maybe hopefully discover the new layer of physics beyond the standard model. So we need a broad, versatile, and ambitious program that at the same time can really sharpen our knowledge of already discovered physics, but that could also push the frontier of the unknown at high, but also at low scales, right? I mean, we all thought for many years that new physics will appear at very high energy, but actually what we have discovered also on theoretical model building is that new physics could show up at much lower scale, in terms of light and very weakly coupled new physics. And this could, for instance, address several issues of the standard model, in particular in dark matter, also, let's say dark matter mostly. Right? So that's why we need really this machine that could probe both light new physics, but also heavy new physics, right? So what is a future circular collider? It's a versatile particle collider with 4 interaction points housed in a 200-meter underground tunnel of a size of the order of 91 kilometers. And it will be built around CERN. Right? And it will be implemented in several stages. First of all, you will start by colliding electron and positron to produce Higgs, electric boson, heavy meson, or also to produce a lot of gluons, right? So it will be really Higgs, electric, flavor, top, and QCD factories that will run between 90 GeV and 365 GeV. And that's what we call FCC-ee, right? So a little bit like LEP, it's a machine with electron and positron. And then, exactly in the same way that we jump from LEP to LHC, we will replace the electron and positron by proton to reach very high energy, maybe 100 TeV, maybe 100 TeV, or maybe only 85 TeV. It will depend a little bit on the magnet that will be available, in 30 or 40 years from now. I will come back to the FCC probably in the third lecture, right? FCC-hh, right? Okay, so it's probably obvious to everybody that we need more energy to probe new physics. But I want also to give you some example that precision measurement of already known object, like, I don't know, the W and the Z, could also be actually a discovery tool, right? And maybe the first and most exciting historical example is actually the discovery of Neptune via the study of the anomalous trajectory of Uranus. Yeah. In the middle of 19th century, there were more and more precise telescopes, and people were measuring with care, the trajectory of all the known planets of the solar system. And they discovered that indeed, in this case, Uranus didn't really follow the Newton's law, right? So already at that time, people were thinking about BSM. They thought, Newton's law are not correct. We need to modify the classical mechanics, whatever. And then there was this French astronomer, a theorist at that time, right? He called Le Verrier. And he had this idea that actually Newton cannot be wrong, right? Instead, there is a new planet that was never observed, right? But is there, and actually the effect of this planet is to modify a little bit the trajectory of Uranus. So he sit down, using Newton's equation, he was able to predict the mass and the position of Uranus, of Neptune. Right? And then he sent a letter to his friend, the experimental friend. At that time, it was the people in Berlin that had the best scientific instrument. Right? So he sent the letter to Berlin. It took 3 days for the letter to travel between Paris and Berlin. And he arrived, and in the same evening, his experimentalist friend, took the telescope. They looked exactly at the point that were predicted by Le Verrier, and they found this new planet. Right? So of course, at that time, it took only 3 days between the theoretical prediction and the experimental verification, and now we are talking about time scale of order 20 or 30 years, right? But hopefully, it will be the same story, right? We will be studying with care already known particle of the standard model, and this will help actually discovering new planet, new particle. There is, of course, other example, right? Because a few years later, the same story repeated itself. With the trajectory of Mercury, the planet which is the closest to the Sun. And at that time also, the trajectory of Mercury didn't follow actually the Newton's law, right? So Le Verrier came out and said, I know, I have the solution. There is a new planet, and I can exactly predict the mass and the position of this planet. So again, he sit down, he sent a letter to his friend, and that time his friend looked for this new planet, and they couldn't find it, right? And indeed, this new planet, Vulcan, didn't exist, but you all know the solution to the problem is actually that at that time, you need to give up on Newton mechanics and go to general relativity, right? So sometimes, indeed, you discover some new planets, some new particle, but sometimes you discover new fundamental laws of physics, right? So there is certainly some value in study with care all the already known particle with higher and higher precision, right? And maybe closer to us, we could also say that the Higgs boson has been predicted or discovered by the careful study of the interaction of the W and Z to the quark and the lepton. Those particles were measured with very great care at lab, and in order to fit the experimental data, you needed to introduce a new particle, the Higgs boson, at a mass which is actually very close to the one that has been observed later on by the LHC. So there is definitely value, is in improving actually the precision of already known theory. And that was the case also of LEP. People complain for some time that LEP hasn't discovered any new particle, but actually, as Erwin Schopper said, when LEP was actually a transformative machine because it really changed high-energy physics from a 10% science to 1% science, right? And probably one of the goals of FCC is actually to go to the per mil level or even below the per mil level in measuring with great care all the standard model interactions. So there is certainly one sector that requires more precision is the one of the Higgs boson, right? Why so? Because simply the knowledge of the value of the Higgs couplings, to all the particles of the standard model, to the gauge boson, to the quark and the lepton, are actually essential to really understand the deep structure of matter and the deep structure of the universe. There is really several fundamental questions that are linked, potentially, this is just theoretical hypothesis at that moment, but several questions that are linked actually to the value of the Higgs coupling to matter, to the standard model matter. The first question is about the lifetime of stars. Why the sun is burning since several billion of years? Well, this is because the W and the Z have a mass of the order of 100 of GeV. If you switch off the mass, then the sun is burning basically instantaneously, right? So you really need the mass of 100 GeV to give the sun a lifetime of several billion of years. And where the mass of the W and the Z is coming from? Well, from the interaction with the Higgs boson, right? And that's really a point that has been established now by the LHC, right? We know that the mass of the W and the Z are essentially originating from the interaction with the Higgs boson. So that's a question that has been solved. Right? We won't come back to that. Maybe we can refine to understand whether all the mass of those W and Z are really coming from the Higgs boson, but that's order of magnitude. This is certainly established, and this is probed now at the level of 10% or so. But there are other fundamental questions. What is the size of the atom, right? What is the size of the hydrogen atom, right? And this is important, right? Because the size of the hydrogen atom at the end of the day controls the size of everything, right? The size of the universe is linked to the size of the hydrogen atom, right? And the size of the hydrogen atom is linked actually to the mass of the electron, right? Remember the Bohr radius formula, there is a mass of the electron appearing there, right? And where the mass of the electron is coming from? Well, according to the standard model, this should come from the interaction between the electron and the Higgs boson. Right? But that's a theoretical hypothesis, right? And physics is about experimental facts. So we need to go and measure this interaction to see whether or not this agrees with the theoretical model. Right? So we certainly need a machine that can achieve this measurement. Right? So the bad news is that the LHC won't be able to do that, right? Simply because those interactions, according to the standard model, is very small, right? Means that the number of events where you could see a Higgs boson decaying into an electron is is very limited, and you won't have enough statistics to actually see this happening in your lifetime. Right? So you need a new machine that can really maybe produce the Higgs by colliding an electron and a positron. Right? There is another question about matter, right? I mean, the stability of matter, the stability of the nuclei. This is due to the fact that the proton is actually lighter than the neutron. Right? And that's not an obvious fact. I mean, the mass of the proton and the neutron is mostly coming from QCD. Right? I mean, we all say that the mass of elementary particle is coming from the interaction with the Higgs. But the proton and neutron are not elementary particles. You know, they're composite bond state, composite of gluon and quarks, right? And actually, the mass of the proton and neutron is mostly strong interaction, is mostly QCD. But you all know that QCD is actually isospin invariant, so you predict the same mass for the proton and the neutron. Of course, in reality, there is a difference between the proton and the neutron, right? The proton is electrically charged, and the neutron is electrically neutral. And this electromagnetism actually gives a mass splitting between the proton and the neutron. But the bad news is that actually QED, I mean electromagnetism, gives a higher mass to the proton compared to the neutron. Right? So that will be a catastrophe because then the neutron will become unstable and decay into neutron. Right? So what saves us is actually the mass difference between the up quark and the down quark. You know that the proton is 2 up quark and 1 down quark, and the neutron is just the opposite. And simply because the down quark is heavier than the up quark, that's enough to make actually the neutron heavier than the proton and save us from decaying. Right? So where the mass of the up and down is coming from? Well, according to the standard model, this is due to the interaction with the Higgs boson. Right? So this tiny mass of the up and down, which is a very tiny fraction of the mass of the proton and neutron, right? Those tiny mass are supposed to come from the interaction with the Higgs boson. So again, that's something that we want to go and measure, right? So we want to build a new collider, again, because this won't be accessible at the LHC. We want to build a new collider that maybe is able to measure those interactions. Good. Another important question is actually about the birth of the vacuum. So the vacuum, which is a state that we live in, right? About a nanosecond or a tenth of a nanosecond after the Big Bang, you know, the universe went into a different vacuum. It went to a vacuum where the universe is actually filled with this Higgs substance, where this Higgs vacuum expectation value developed something like 10 to minus 10 seconds after the Big Bang. But what is the dynamics of this phase transition? You know, from a universe which is empty to a universe which is filled with this Higgs substance. Right? That's a very dramatic phenomenon that occurs in the early times of the universe. Right? And nobody was there to take a picture because, you know, light didn't really exist at that time. So there is no picture, there is no telescope that can answer this kind of question. Right? But the dynamics of this phase transition is actually controlled mostly by actually the way the Higgs boson interact with itself. So we want to measure the shape of the Higgs potential. Or most likely, I mean, it won't be simply, you know, a single Higgs boson. Maybe there is an extended Higgs sector, whatever. But we need to measure, you know, the potential of all this scalar field that really control the dynamics of this phase transition. And for that, we need, the first step is really to measure the way the Higgs interact with itself, right? So there, actually, iLumi LHC will make great improvement, right, in measuring the Higgs self-couplings, the triple Higgs self-couplings, probably at the level of 30 or 25%. That might be enough to really distinguish between a second-order phase transition and a first-order phase transition, right? We want to know, for instance, if at some point, you know, the universe boils, like exactly when you are boiling water, you know, create bubbles and bubble collide and maybe, you know, produce gravitational waves, something like that. But clearly, we want to measure this Higgs self-coupling as accurately as possible, and we need, again, a new machine that can study with great care the Higgs boson. And another important question is about the imbalance between matter and antimatter, right? You know that in principle, I mean, according to the laws of physics, after the Big Bang, we should have an equal amount of matter and antimatter, but of course, during the evolution of the universe, you know, we are left only with matter. All the antimatter disappear and annihilate with matter, right? So where this imbalance is coming from? Well, most likely, you need some interaction at some point that violates this matter-antimatter symmetry, which is called CP symmetry. So in the standard model, there is two possible sources of CP violation. There is a phase of the mixing between the quarks, the phase of the Kabibo-Kobayashi-Maskawa matrix, but the net effect of this phase that violates CP is actually very suppressed by the masses of the quarks, the tiny masses of the quark, and the small value of the mixing between the quarks. Right? So you certainly need another source of CP violation. And actually, this extra source of CP violation could come from the interaction of the Higgs boson with the quarks and the lepton, or also to the gauge boson. Right? So we certainly want to measure the possible source of CP violation in all the interaction of the Higgs boson with the standard model particle. Right? So that's again something that the LHC, and in particular the high luminosity LHC, will start doing, but we need another machine that will do some much more precise measurement than that. So yes, high-lumi LHC will make remarkable progress. I mean, at the end of the day, high-lumi LHC will be producing something like 100 million of Higgs boson. So it's already on its own, a Higgs factory. But you all know that LHC is a hadron machine, so there is a huge background, and you need, to design cuts, etc., to really see the signal, right? So at the end of the day, you will see maybe 10,000, or maybe if you're lucky, 100,000 of Higgs boson, right? But we want a machine that can reach, maybe the per mil level, so you need at least 1 million of Higgs boson. So you need to build another Higgs factory, most likely an E plus E minus factory, where the signal is clean out of background, so you can really produce all the Higgs boson and observe all this Higgs boson in your detector. Right? So the goal is to build a machine that can produce more than 1 million of Higgs boson that you can see and analyze and study. Right? So a new collider is needed. Right? So I will discuss in more details, all the Higgs physics probably in the lecture tomorrow, but this is just a snapshot of what FCC can actually achieve, in the measurement of the various coupling of the Higgs boson to the particle of the standard model, the coupling to the W, the coupling to the Z, to the gluon, to the photon, etc., etc. And you can see here the improvement compared to the sensitivity which is expected at the end of high luminosity LHC. Right? So in short, there will be really a sub-percent precision for most interesting couplings, often with an order of magnitude improvement compared to high luminosity LHC. And for the first time, for the first time ever, you will have access to the second generation quarks, for instance, the Higgs coupling to the strange or to the charm quark. You will also have, a measurement of the Higgs width at the percent level. And the good thing is that this measurement of the width will be model independent, right? At the hadron machine, you cannot, the only thing that you can measure is actually the cross-section times the branching ratio. So you don't really have direct access to the width of the Higgs boson. You need to make hypotheses, assuming that, for instance, there is no additional exotic decay mode for the Higgs boson or things like that, right? Under this assumption, you can maybe bound the Higgs width. But if you really want to have a model-independent way to measure the Higgs width, you need an E plus E minus collider where you can really control the energy of the beam, right? The beam, the colliding beam. And this will also allow you to measure the mass of the Higgs boson at the level of 4 MeV, which turned out to be actually the size of the width of the Higgs boson, right? And that will be essential later on, maybe if you want, to measure the electron Yukawa, you really need to measure, to control the mass of the Higgs boson at the level of the order of its width, right? And then another interesting thing, which is really unique to FCC-ee, is actually that for the first time, you will have enough statistic to see the direct production of the Higgs boson as an S-channel resonance from a collision of an electron on a positron. Right? And what is really remarkable is that you can achieve all this Higgs program in a very compact period of only 8 years of operation. If you compare to all the Higgs factories that have been discussed, in particular during the European strategy process, there are some projects that need 20, 30, or even 50 years to actually achieve measurement at the comparable level. Right? So this is good, because you don't take so much time to do X physics, which means that you have enough time, to do something else in life. I mean, you can do flavor physics, you can do QCD, you can do, I don't know, BSM, searching for light and exotic new particle, etc. Right? So it's an X factory, but it's an X factory that can do also many other things. And that's really the broadness of the physics program of FCC that makes it very appealing. Right? At the end of the day, you have to remember that the way we discover general relativity was not by studying very carefully Neptune, it was by studying carefully Mercury. So not the latest discovered particle, right? But actually the particle or the planet that was known from a long time. So maybe the same story will repeat. I mean, we won't need to study very carefully, more and more carefully, the latest discovered particle of the Standard Model, namely the Higgs boson. But maybe, we need to study with very great care the old and good particle of the Standard Model, in particular the W, the Z, the AV mesons, the Kaon, whatever, the B mesons that are there for many years, but we haven't been able to measure all their properties with enough accuracy, right, to reveal new physics, right? So that's really, I think, the great advantages of a machine like FCC-ee is really that it's a very broad and versatile machine that can do a lot of different physics at the same time. Right? So clearly it's X factory and is doing very well in measuring the X properties, but it can also do a lot of different things. Good. So now I would like to take a few minutes actually to tell you a little bit about the process of the feasibility study, right, that took place from 2021 to 2025. And yes. So this feasibility study actually is a result of the previous European strategy update, which concluded in 2020 that an electron-positron X factory is actually the highest priority next collider, and maybe with the ambition on a longer term to run a proton collider at very high energy. Right? So that was a recommendation of the community. This European strategy is really process is really a bottom-up process, right? It's a community that meets together, make recommendation, and then it's up to the manager to decide whether or not to follow those recommendations. So in that case, the CERN Council actually approved the recommendation and asked the CERN management to implement those recommendations. So that's why the feasibility study was launched in 2021. It has been completed in April 2025, and there had been a midterm review in 2023. So what was the objective of this feasibility study? First of all, to demonstrate that it's feasible to construct such a machine. So what does it mean, feasible, right? You need to make sure that you know the land where you will build this collider, right? There is a geological study. There is some technical studies. You need to understand exactly what kind of accelerator, detectors, etc. that you need to build. You need to make sure that you will have all this administrative authorization to go ahead and do the study and maybe later on, build this collider. But there is also the question of where you want to put this collider, and I will come back to that in a moment. Basically, the size of this collider was clearly decided in view of building this 100 TeV machine with proton later on. So this sets the size of about 100 kilometers. But where do you put this 100-kilometer tunnel? Near Geneva, near CERN, right? There is a lot of constraints that are not so easy to cope with. Right? So that was really the first part, right? Make sure that you can build this ring and that you have all this authorization to do it. Then there is all this discussion going on with the host state, right? Because at the end of the day, 100-kilometer tunnel cannot sit in CERN land. CERN can do more or less what it wants on site, but when you need to go outside CERN land, you need to get the authorization, right? And there is a lot of discussion going on with France and Switzerland to make sure that they agree to go ahead with this construction. Then there is a question of the optimization of the design of the collider and all the injector chain, right? And then you need also to make sure that you have enough energy, enough resources to actually run this collider, without emitting too much carbon dioxide in the atmosphere, or without using all the electricity which is available near Geneva, right? And then the next question is, of course, how much does it cost, right? Can this machine be affordable within the CERN budget or not? And actually, it was clear from the beginning that probably you need to secure external resources outside CERN, right? So that was also part of the mandate to really look for extra money from various maybe new countries that will join CERN, or maybe by private donors that will be happy to fund some fundamental research, right? And then at the bottom, there is also the question of the physics. Why do you want to build these colliders, right? I mean, you need to really consolidate the physics case and also understand what kind of detector you need to build to actually be able to achieve all the measurement that you're interested in. So about the question of this placement, right? Where do you want to put this 100-kilometer tunnel? So here, there are first of all, few external constraints. I mean, the fact that you are living in a very densely populated area. You are not in the middle of China where there is nothing around. Here we are near Geneva. And also there are various mountains, right? Here there is the Jura, there is the Alps over there is the Salève, and there is a lake, right? And also in this region, it's protected, environmental protected area because there are various frogs or whatever, various animals that live there, and animals that don't really like physicists, right? So you cannot go and do physics in this area over there, right? Yeah, you cannot clearly go under the mountains. I mean, because you will require a very long shaft to actually access the tunnel, right? So you want to stay in a region with low altitude, in a sense, right? No big mountains. And there is also consideration from the fact that, for instance, you want a perfect symmetry among all the interaction points, right? So this means that as soon as you decide where one interaction point is, all the other interaction points are fixed, right? So in particular, you say, oh, maybe, I would like to have one interaction point here, right? But then the other interaction point will be in the middle of the lake, which wouldn't be very convenient, clearly, right? So there is all this sort of consideration, that makes life a little bit more complicated than originally thought, So at the end of the day, people looked at that. I mean, maybe they use AI or not, I don't know. But at the end of the day, they draw many cycles, of different size. And they concluded that they couldn't accommodate actually a 100-kilometer tunnel, but the most optimal size was something like 91 kilometers. Actually, there is a quiz here. As I say, there is 4 interaction points: PA, PD, PG, and PJ. And if you know a little bit the geography around here, you should be able to recognize where the placement of this experiment will be, right? So there will be one in Ferney-Voltaire, which is kind of obvious, and the other one maybe a little bit more remote from CERN, so less known from the CERN users, right? So these are the 4 interaction points. And in addition, there will be also 4 additional technical area, technical shaft, where you want to be able to access the tunnel to bring down material, whatever, maybe bringing down some people also. Well, but the 4 experiments will be really located in these 4 interaction points: PA, PD, PJ, and PG. Right. Good. So, as I say, there have been a lot of studies going on over this few years, really to really understand the underground structure of the land. In particular, there have been experiments like that, big machine going around your garden to really shake the earth and understand actually the structure of the land behind it. There is even some weird chip going on the lake, to really understand the structure of the ground below the lake and understand whether there is still water or not, and things like that. Because, the worst things that you would like to do when you are digging this tunnel is really to encounter water, right? That will be a disaster. You need to freeze the water to remove it, etc. So that's as much as possible. You want to avoid any source of water in the land. So there have been a lot of studies going on, and so far, no showstoppers have been encountered, and there is really understanding that you can go and dig this tunnel around this 91-kilometer path, right? Then the next question is actually, what do you do with this excavated material? So you want to dig this 91-kilometer tunnel, the size of the tunnel will be 5.5 meters. So at the end of the day, if you do the math, you will get something like 6.5 million cubic meters, right? So what do you do with this excavated material, right? You don't want to put it in the garden of your neighbor unless you don't like it, don't like those neighbors, right? So there have been various studies along this line. For instance, there is this project which called Mining the Future that concluded in this open sky laboratory that actually looked at what to do with this excavated material. So the excavated material is mostly molasses, which is totally fertile, right? So you cannot, in priori, do anything with this material. But this project actually tried to mix a little bit this molasses with some microorganism like some fungi or whatever, and then they make this excavated material fertile. So you can use it later on to do some agriculture or maybe to grow some plants, right? And this is exactly an experiment that has been going on near P5 in CECI. So this is excavated molasses that you put on the surface, and then you mix with this microorganism, and you can indeed grow some plants or whatever. And one experiment has been done, I mean, in order to grow, for instance, some flower. And in the last FCC weeks in Vienna, I mean, the people responsible for this project came up with some roses that they offered to Fabiola, right? Just as a proof that indeed it works and you can do something out of this excavated material. Right? So that was the first part of the environmental consideration, but there is other things later on that show up also in addition to the excavated material. When you will be running this machine, you will be certainly producing some heat. What do you do with the heat, right? So certainly you can offer some heat, to the local houses, to the school, to the swimming pools, in Ferney-Voltaire, whatever. And that is already happening now. But what do you do with the heat, in particular in the summer? At the end of the day, those machines won't really run in the winter when the price of electricity is very high. It will mostly run, in the warm seasons. Fortunately, there are actually people interested in heat in the summer. These are all the cheese factory, right? In order to grow some comté, whatever, some Tome de Savoie, you need actually some heat. And there have been a lot of discussion going on with all the cheese factory in the Jura and Haute-Savoie to actually reuse the heat that will be produced by FCC. Another interesting point was actually how to integrate this machine with the local infrastructure, right? In particular, you want to bring people, experimentalists, down to the tunnel, or you want also to bring out all this excavated material. So somehow you need to connect the tunnel with the existing roads, right? And actually that was part of one consideration of the optimization of the layout. Where do you put the experimental point? You needed to minimize the distance with the existing highways that are already there in the region, right? So you see all the highways, that goes to Chamonix, whatever. And here, this experimental point have been conveniently located close to these highways, in such a way that at the end of the day, you need to build less than 4 kilometers of new departmental road to access all the interaction point and the technical shafts, right? So that's really remarkable. Another thing is about the connection to the electrical grid, right? You need to bring electricity and power to this machine, making sure that when you turn on the machine, you don't switch off electricity in Geneva, right? So there have been a lot of discussion going on with this French electrical grid operator, RTE, right? And also you want to have some redundancy in the power source, in case there is a problem with one source of electricity, you want to make sure that you have enough electricity still coming up in the machine. And that has been done in the discussion here, right? And here you can see actually the power consumption of this machine. I will come back into the run plan in a minute, but there will be different energy stage of this machine. Actually for FCC-ee, you will run between 90 GV at the Z pole, and you can see here the electricity consumption, about 1.2 terawatt-hour per year, and up to the TT bar threshold at 365 GV, where the power consumption will raise to 1.6 terawatt-hour, right? per year. This connection to the electrical grid has been also optimized in view of later on of FCC-hh that might need actually a little bit more power than what is required for FCC-ee. So, people have already anticipated that FCC-ee will be followed by FCC-hh later on and, design all the construction accordingly. In the meantime, of course, there is a lot of R&D that are going on actually to minimize this power consumption, in particular in a study of the magnet that will be able to run at higher energy, so consume less energy in cryogenic or whatever. In such a way, I mean, the latest development is that FCC-hh will basically have a power consumption which is of the same order as the TT bar run of FCC-ee, or a little bit more maybe, but not dramatically more. Then the next discussion was about civil engineering, right? So I told you that there is a 91-kilometer tunnel. So this is a cycle, but you can always draw it as a line if you like it, right? So this is actually the structure of the underground, tunnel. And here you see that, there is this 8 shaft that you need to build, right? And the depth of this shaft varies between 50 meters, I think probably A or B are the smallest one, up to the largest one, which is something like 500 meters deep, right? And you can see that clearly the tunnel will go in particular under the Lake Geneva here, but deep enough in such a way that you go below the water. And the interesting things to look at on this diagram is actually most of the structure of the land is actually some morass, which is very easy to dig with this tunnel boring machine, right? That you will use this tunnel boring machine to dig this tunnel, except maybe in this area that cannot be avoided, where the structure here is limestone, which is a little bit more complicated to dig than the morass. So really, the tunnel layout has been optimized really to maximize the amount of morass and minimize the amount of limestone. Right. So I already told you that there will be 4 interaction points plus 4 service area. At each of the interaction points, actually, you will have 2 shafts. I mean, mostly for security reasons. When there are experimentalists working in the detectors, you need to have escape routes. So you need 2 shafts. So this means that at the end of the day, you will have a total of 12 shafts. So I've already told you that you will use these tunnel boring machines, which are huge machines that progress into the tunnel, so they dig, and at the same time they put concrete. So once the tunnel boring machine passes by, basically the tunnel is ready to be used, right? And they will progress at a rate of 18 meters per day in the morass. So you will have 8 of them, 8 of these tunnel boring machines that are coming down in each of the experimental points, PA or PD. You bring down 2 of those tunnel boring machines, and they progress in opposite direction. And they will meet in this service area, right, in B, for instance. Right? So at the end of the day, if you do the math, you need at least 2 years to really dig this 91 kilometers. Right? And yes, so I told you that you will have those 4 interaction points. So this means that you will have 4 caverns. So people are envisioning 2 small caverns of the size of CMS and 2 large caverns that will be something like 60 or 65 meters long. Right. And you can see here some drawings. So there will be the experimental cavern connected also with the service cavern where all the machine will go through. Okay, so what is the timeline? So this is a timeline of the discussion that are going on at the moment with the operant strategy, right? A process that was launched, about a year ago. The first submission happened, were collected by the end of March, in particular this feasibility study report, right? And there have been this big open symposium in Venice at the end of June. And then there are many people working hard in order to produce this briefing book that will compare the various projects with each other. And then at the end of the day, it's expected that the operant strategy group will come up with some recommendation toward December, whatever, and they will be hand out to the CERN Council sometimes in March or in June. Right? So that's hopefully the end of the process of the recommendation, and people are expecting that the recommendation will be positive towards FCC. Then we can move forward and take those recommendations and really prepare for the next phase that will be basically the design of the detectors and construction or progress towards the collaboration, the various collaboration that will take place at the 4 interaction point. Right? That's the first phase. I mean, if everything goes well, the FCC project will be officially approved by the CERN Council in 2028. The construction will start in 2033. It takes basically 5 years to get all the authorization, to come up with a clear financial plan, collect all the money that you need. So you really need these 5 years between the approval of the project and the start of the construction. So the construction will take about 8 years. You need some time to dig the tunnel, to dig the shaft, to bring down all the installation, whatever. And then you really expect the first collision to take place in 2045 or so. And then FCC-ee will be running for 15 years, until 2060. Then again, you will dismantle FCC-ee and switch to FCC-hh that could start operating around 2070 or 2075, 2080, right? Until 2100 or so. Right? So we are really talking about a project that could span something like 70 or 80 years from now. Right? So what was the feedback, right? I mean, the feedback from all this feasibility study. Well, there were, last year in 2024, there was this statement of the US, still under the previous administration, but okay, there is no indication yet that there is a change in policy, right? So the US say that if CERN actually decide to go ahead with FCC-ee, then the US will join and contribute to the construction and the operation of this machine. And 1 year later, I mean, Canada came up with a very similar statement, just to show that Canada is still an independent country and not a 53rd state, right? So very similar statement. Earlier this year, there have been also some further progress towards the US community, in particular the US National Academy came up with this report, about elementary particle physics, a report which is submitted to the funding agency, but is also sent to the Congress, right, to the US Congress. And there are 2 main recommendations of this report. The first one is that, people in the US would like to have another collider, and maybe they're thinking about a muon collider that could start operating in 2050, 2060 or so. But in the same time, they also understand that probably the next collider after the LHC will take place at CERN in Europe, and they really recommend the US people, the US community to engage into the future circular collider. Right? So that was really a clear breakdown of the degeneracy between various X factory projects. They really recommend FCC as the top priority for future X factory. And indeed, I mean, a couple of weeks ago, there have been this change of organization within DOE. They switched from an X factory coordination consortia that were really study the various X factory on an equal footing, and now they switched to the X factory circular collider, right? So they really made the choice and decided that the next project should be FCC at CERN. Right? So you can see here the organization of this DOE study for FCC. That was from the other side of the Atlantic, but clearly in Europe, I mean, there have been also huge interest. I mean, in particular, in September 2024, there was this interesting report by Mario Draghi that was thinking about how to keep Europe competitive compared to the US and competitive compared to China. And they came up with various recommendations, and clearly in this report, I mean, they really noticed that CERN was an essential element to keep competitiveness of Europe. And indeed, I mean, CERN is mentioned 90 times in the report, and FCC is mentioned 3 times. Right? If you were around, I mean, last November, I think, I mean, Ursula von der Leyen also showed up at CERN for the 70th celebration, right? And she had a very nice word about FCC, right? And this actually materialized in a very concrete proposal last July. The Commission, the EU Commission, made up a proposal for the next multi-annual financial framework, right? And here they identified 11 moonshots, that are essential for Europe to remain competitive. And the good thing is that, you know, they can provide up to 20% of the budget of the project. So for FCC, I will mention maybe the budget tomorrow, but the budget is of the order 15 billion, so 20% will mean 3 billion. So we can expect 3 billion by EU as a contribution to the CERN project. And here are the 11 moonshots that are identified in this report, and you can see that here FCC is actually the project number 1 compared, I don't know, to clean aviation, quantum computing, AI, whatever. Right? So hopefully things are progressing well, and we can hope nice development. There were also support at a more local place. I mean, you know that probably in November 2023, you know, Fabiola actually hosted the French president and the Swiss president, and here again, I mean, Macron said that it was really important for CERN to continue his exploration, really to keep the leadership in particle physics and in technology development in Europe. Right? So there is certainly some political support for this project. Okay, the thing that the politician cannot understand very well is the physics. So they understand the competition with China, with the US, but they rely really on the physicists to make this project interesting for physics. So here I would like to give you a snapshot of the physics that can be achieved at FCC. So these are the main parameters of the machine at the 4 energy points that will be explored by FCC-ee. So as I said, there will be a run at 90 GeV, a run at 160 GeV, another run at 240 GeV to produce about 2 million of Higgs boson, and another run at 365 GeV to produce a pairs of top quark. Right? So you can see the various parameters and the number of bunches per bin, you know, something that varies between 60 and 10,000 or so at the Z. And here's the current, the beam current, etc. So, but to really understand the physics case of FCC, you need to look at this plot that shows actually the luminosity as the function of the energy in the center of mass. And what is really characteristic of all the circular collider is, of course, that this curve will be a decreasing luminosity as a function of the luminosity. But of course, you should look at it in the other direction, saying that if you run at low energy, then you have very high luminosity. Right? And here you can compare the luminosity of a machine like FCC-ee compared to a linear collider like ILC in Japan, or this linear collider facility at CERN that people are dreaming of. Right? So you see that basically up to 500 GeV or so actually is more advantageous to have a circular collider, right, compared to a linear collider. And really the most dramatic difference is at very low energy, something like 90 GeV, where you can produce S as a resonance of E plus E minus. And in this case, you know, if you look at the luminosity here and, you know, run the machine for a couple of years, you will accumulate something like 10 to the 13 Z boson. Right? 10 to the 13 Z boson is 6 orders of magnitude more than at LEP. Right? So just to give you a magnitude, right, an order of magnitude, all the LEP1 data that took 10 years to be accumulated will be reproduced every second minute when the machine will be up and running. Right? Right? And what is really remarkable is that actually, you know, the power consumption will be about the same as LEP. Right? It's not that, you know, you put more power into the machine. No, the power is about the same, but you get 5 or 6 orders of magnitude more than at LEP. So that's really a measure of the progress that has been accomplished in accelerator physics over 20 or 30 years. Right? So this is a plot that shows indeed the luminosity per, let's say, terawatt or whatever terawatt that you are using. So the luminosity per terawatt you know, as a function of the energy in the center of mass. And you can see here that at 90 GeV, you have this 5 order of magnitude difference between LEP and FCC. And basically, even at energy close to 200 GeV, you still have 4 orders of magnitude. Right? So those machines are really fantastic machines that came out of progress, you know, accumulated over the years in running various colliders. For instance, you know, you are using this double ring collider that makes many bunches, high current, exactly like what you're doing at LHE, also in B factories. Right? So this is the main difference compared to LEP. So with top-up injection, so this is again a standard now at modern light source like this SLS. Or it's also used at E+, E- collider in the US, in Japan, or in China. There is this crab waste collision scheme that also increase the luminosity. And then you are using some superconducting radio frequency systems with different operation mode, in particular the Z, that increase even further the luminosity, right? This reverse phase operation that are really essential at the Z. So what is the run plan? So now you have a plot like this, and now you want to design actually how much time you will spend at the different energy points. So I already mentioned that there will be essentially 4 energy points at FCC-ee, one at 90 GeV, another one at 160 GeV, at 240 GeV, where basically you have the maximal cross-section for the production of the X in association with the Z. And then you want to reach also the 365 GeV, where you can produce a pairs of top quark, right? And now it's, people are thinking of running something like 4 years at the Z in order to produce this 10 to the 13 Z boson, 2 years at 160 GeV to produce, 2 10 to the 8 pairs of W, and then something like 3 years at 240 GeV to produce again 2 million of X boson, in association with the Z, but also 60,000 X that are produced by fusion of W, right? It's another production mode of the X. It's certainly less important in terms of quantity, but it brings additional information that will be useful in extracting all the value of the X coupling. And then you can run, as I say, at 360 GeV for something like 5 years to produce 2 million of pairs of top quark, but also to produce something like 400,000 X boson in association with the Z. And it will be important to actually produce the X boson at 2 different energy, at 240 GeV, but also at 365 GeV. It will help actually to disentangle degeneracy in the extraction of the value of the X couplings. Very remarkable progress that took place, very recently during this feasibility study is actually that you can use the same RF system, between 90 GeV and 240 GeV. So you can basically, switch the energy or change the energy in almost instantaneously between those 3 different energies. Right? So that gives us a lot of flexibilities, actually, because maybe you want to start to run at the Z, and then you go to calibrate your detector, and then you go to the ZH, and then you want to go back to the Z to check a few things, or also because it's a very demanding run, so you need to control everything. When you will be accumulated something like 10 to the 13 Z boson, you need really to have a good control of your detector. So it will be a challenge, and you don't want to waste 5 years of your time at the beginning to devote it to these studies. Right? So it's better to go a little bit at different energy back and forth to really optimize your physics program. Right? So this is really possible thanks to this 2-cell cavity system that can be really used independently from 90 GeV to 240 GeV. Then if you want to reach the 365 GeV, then you need to install all the cavities. So it will be another RF system that you need to bring down into the tunnel. Right? Good. Yes. So this is a run plan. I mean, this, in principle, that will be the logical order. You start running by 4 years at the Z, then you switch to WW, then ZH to the top. But actually, you can really optimize things, right? And maybe a more convenient thing will be to run maybe for 1 year or 6 months at the Z in order to really calibrate your detector, then to go to the WW, then to study the X, and then to come back to the Z later on, right? So again, this is something which is feasible now that you have a machine which is really flexible enough to change back and forth with the energy. But really, the remarkable aspect of FCC is really that it has a very rich physics program, which is achieved in a very compact period of 15 years of operation. You will do a lot of different physics in those 15 years, right? And actually, here is a snapshot of the physics that you can achieve at FCC-ee. So again, it will organize in different energy points. There will be clearly the X factory aspect. You want to run at 240 GeV to produce the X, to measure the mass of the X, to measure the width of the X, to measure all the coupling of the X, to measure the X self-coupling also in a way that I will discuss tomorrow. There is a run at 365, which is obvious, to measure the top properties, the top mass, the top width, or the electric top coupling that will be essential later on when you will be running the FCC-hh machine. You will need to know with great accuracy all the electric coupling of the top. That's something that you cannot do at FCC-hh, that information that you will need to gather from FCC-ee. Right? And then there is what I call this intensity frontier run of FCC-ee, which comes from producing this 10 to the 13 Z or 10 to the 8 pairs of W's. Right? So what can you do with all these objects? First of all, you can really reproduce and improve all the electric precision measurement. So measure the mass of the Z, measure the width of the Z, the number of effective neutrinos, this forward-backward asymmetry, the mass of the W, etc. So you will improve by something 3 orders of magnitude in precision compared to the lab precision measurement. Going from 10 to the 7, 10 to the 12 Z is basically 10 to the 6 in terms of number of events, so 10 to the 3 in terms of precision in the measurement, in terms of sensitivity. But there will be also a lot of QCD measurement that you can achieve at running from the Z or even below the Z. First of all, you will be measuring the value of the strong coupling constant, alpha QCD, with a per mil accuracy. And that's really important, to calibrate and to get a very clean prediction of all the cross sections, right? So you want to control all the parametric uncertainty in your theoretical prediction, and one key parameter to control those parametric uncertainty is certainly the measure of alpha strong. So that's something that you will achieve via some method that we will be discussing tomorrow or on Thursday. But then there is also some other non-perturbative aspect of QCD that you can achieve with FCC-ee. You can measure the quark and the gluon fragmentation function and do some clean non-perturbative QCD studies, some jet clustering things or things like that. So the other interesting aspect of this intensity frontier is actually the direct search for light new physics. I told you at the beginning that you want a machine that is able to probe the high energy frontier, but also this low energy frontier. So how do you do that? Well, you do that by producing those 10 to the 12 Z boson, right? And then those 10 to the 12 Z boson, might couple to very light, very weakly new physics, in such a way that you will observe some very exotic, very rare decay mode for the Z boson, right? But you have so many of them that you will be sensitive to those very rare events at the level of 10 to minus 10, 10 to minus 12, right? So this is the case, for instance, if you are interested in searching for right-handed neutrinos, that might be connected with a CESO mechanism or not, right? So that's a plot that shows actually the sensitivity of FCC-ee here, right? In terms of the mass of those right-handed neutrinos, and here on the y-axis you have the mixing angle with the active neutrinos. So here you can see the existing bound from LHE or even the beam dump experiment like SHIP that you expect in a few years from now. And you can see that FCC-ee will actually extend those existing bounds, right? Actually will extend in a region which is actually fully interesting in the sense that it's a region, in the white region here above the red band, is a region which is compatible with the CESO mechanism. So what is really remarkable for me actually is that FCC-ee actually in this region around 40 GeV really fully cover the parameter space that could explain the mass of the neutrino. So certainly is doing better than the other machine, but is also achieving the job, right? In the sense that you will say yes or no whether those right-handed neutrinos exist in this mass region. So this is the case of the right-handed neutrinos, but you could draw similar plot for axion-like particles, for dark photon or whatever, some long-lived particles. Right? All these things have been studied, and I will show some example on Thursday. Then the third aspect of having those 10 to the 12 Z boson is actually all these flavor factories, because the Z will decay into B quark or charm quark, and you will actually produce many of them, something like 10 to the 12 pairs of B or charm quark. This means that you can really do a lot of B physics with a data sample which is larger than any other flavor factories. Right? So you will certainly be measuring some forward-backward asymmetries of the B quark or the charm quark, but you will also be able to measure some CKM matrix element, in particular VCB. You need to look at the decays of the W, and that's something that can be achieved in this FCC machine. You will also be probing CP validation in the neutral B methods, right? And another aspect is actually in the tau physics, right? I mean, again, from the decay of the Z, you will produce many pairs of tau leptons in such a way that you can actually achieve electric precision measurement, now not using electron or muon, but actually using the tau leptons, right? And you will be able to use or improve the test of lepton flavor universality in the tau sectors. So this is really a snapshot of all what can be done at FCC, right? But of course, you need to design the right detector to actually achieve those measurements, right? And there are various characteristics associated to all the physics that you're interested in. For instance, if you want to do electric and QCD, you need a good particle flow, a good energy resolution. If you want to look for light and weakly coupled new physics, you need detectors that are highly hermetic. You need a good tracking and calorimetry. If you want to do flavor factory, you need a good momentum resolution, a good tracker, a good vertexing, a good tagging, etc. Right? So all these aspects have been quantified. There is various tables in this feasibility study report that really quantified all these different requirements coming from the physics. Right? I won't go into the details for this table. I mean, you can look at the report yourself. And then the next step is, of course, to just design the detector that will achieve this measurement. And at the moment, there are 4 detector concepts that are emerging, or sub-detector concepts. For instance, there is SLD, which is using a full silicon vertex detector and tracker. There is idea that you instead use a crystal electrocalorimeter with dual readout. There is Allegro, which is using this noble liquid electric calorimeter, and there is also this ILD that use actually a large volume time projection chamber, TPC, right? So there are some element, very characteristic element that are emerging in this detector concept, and the community is trying to build around those elements, right? So there are not yet collaboration, with locked-in design. There is really a lot of progress which is expected in the next phase between basically from now until 2033, where we expect actually to have clear CDR from the various collaboration that will populate those 4 interaction points. And I see that my chairman is getting nervous, so I will stop here. And maybe tomorrow I can discuss a little bit more, the other thing that you can achieve with the collider, but also use FCC actually differently, maybe as a light source, right? There is other physics opportunities beyond collider that FCC-ee can provide. Okay, thanks a lot.
Okay, thank you very much, Christophe, for the great view over the landscape of FCC. The floor is open for discussion, and I ask those online also to indicate if they want to comment. Please, we start here.
Thanks for the really nice talk, Christophe. I especially like your analogy with the discoveries with planetary observations. I will shamelessly steal this and use it in my own talks. I have a very simple question on your slide 13, where you discuss the tunnel boring operation. So this is something that I have tried to understand before, but never did. A very simple thing. We have 8 shafts.
Yes.
Why don't we lower down 16 tunnel boring machines and halve the time of excavation?
first of all, I mean, I think there is a cost. I mean, each boring machine, you know, comes with a cost, and also you need to secure, you know, those tunnel boring machines, which are not that obvious. I think at the moment there is not a single company that can build this tunnel boring machine in Europe. You need to buy it from China. And then I think it was, I don't know, concluded that it was easier, you know, if this tunnel boring machine actually meet in this technical shaft.
Okay, yeah, they would meet there. Okay,
so you have two of them, you know, you bring two of these tunnel boring machine in the experimental point, and then they progress in the opposite direction, and then they will meet clearly in this technical shaft. So then they will bring.
Maybe they don't have reverse gear, so they have to go just forward. Okay, thank you.
Please open the microphone.
I can hear you, but.
Yes. Yeah. So thank you for the nice talk on this. So I'm just asking you, is there any possibility of running the FCC-ee in polarized mode?
So in principle, yes, but it's always a compromise between, you know, polarization and luminosity.
Right.
So, I mean, the study that we perform is that in principle it's doable, you know, to have this transverse polarization of electron and positron, but then, you know, you will lose a lot of luminosity, so that would not be advantageous. Of course, you have longitudinal polarization that you can use, in particular in the decay, right? So that's not an issue. So here, really, I mean, the focus was more on luminosity than on polarization. But I mean, you are right that in a sense, I mean, polarization is easier at a linear collider than a circular collider. There is some ideas, you know, to inject beams that are polarized at the level of the booster and things like that. But again, the price to pay is luminosity. So.
Okay, thank you.
Please in the back, but wait, I give you the microphone.
Thank you very much for the nice, fruitful talk. Could you please let us know about this question? Why has it been considered for the electron-proton phase? It is decided not to be considered at the FCC?
Well, it's not that it's not considered, but, you know, to look at electron-proton, you first need to have a machine with electron and a machine with proton. So if that happens, it will come after FCC-hh, probably. So it will be in a too far distant future to really think of who will be available to make this experiment at some point. But yeah, it's not part of, you know, baseline design, whatever, but people have that in mind. I mean, at some point, it's an option that might happen in 22nd century or whatever, 22nd century, right? So it's not excluded, but it's not the priority, let's say.
Please. Yes.
Hello. Thank you very much for your very interesting and comprehensive talk. I have two questions. First, you mentioned an FCC briefing book that you were working on, or that the...
Well, the briefing book is part of the European strategy. So is this physics preparatory group, you know, which is a quantity with various people that are, you know, taking all the input that were submitted to the European strategy and provide, you know, this briefing book to the European strategy group that will draft the recommendation. So this is not from FCC directly. I mean, FCC has submitted the feasibility report as an input, and then this is taken up by the PPG to write the briefing book. Right?
Okay. Then another question. I heard that the LHC cannot be reused in the injector chain.
So,
or is not considered anymore to be part of the future injector chain, and I was wondering why that is.
It's not an injector chain for FCC-ee. It might for FCC-hh.
Okay.
This is still under consideration. It's not excluded, but for FCC-ee, we don't need the LHC for that.
Yeah, but for FCC-hh, there were apparently some doubts, as I heard, but maybe...
Yeah, this is still under study, I would say. There is no clear decision on that point.
But what does it depend on? How can I understand whether it's suitable to keep the LHC in the injector chain or not?
Well, I mean, it's various considerations. I mean, the cost, the efficiencies, and things like that, right? I mean, and it also depends at the end of the day the magnet that will be available for FCC-hh. So, if you have a machine that runs at 85 GeV or a machine that runs at 120 GeV, you need different injectors, right? So,
yeah. Okay, thank you.
Please.
Hello. I wanted to ask about the Yukawa couplings to the first generation fermions.
Yes.
So you mentioned the importance of measuring the couplings to the lightest quarks. But will either FCC-ee or HH give us any evidence or observation of Yukawa couplings to the U and D quarks? And could you expand the second part of the question? How tantalizing is the electron Yukawa? Is it really within reach? Do we know yet?
So, I mean, I will come back to this plot and to this question tomorrow. So you see here, actually, that this run at 125. So 125 is the mass of the Higgs, so you really run and sit at the resonance, right, where you want to produce the Higgs as a S-channel resonance of E plus E minus. And you can notice here, this is in blue, which means additional opportunity. So this is not part of the baseline at the moment. At the moment, the baseline includes this 4 energy run at 90 GeV, 160, 240, and 365. The run at 125 is something that you can do in addition, right? So the current projection, I mean, we have experts, in particular David here. The current projection is that if you want to reach a standard model sensitivity, you need to run at 125 for 4 years, right? So, I mean, it's a question whether, you want really to devote 4 years, of this machine, of this project, to really reach a standard model sensitivity. On the other hand, you may say that, factor 2 compared to the standard model is enough. I mean, the current bond is something like 500 times the standard model, right? I mean, that's the projection at the end of ILUMI LHC. We won't know better, I mean, we won't know the Yukawa of the electron with a factor 500 more compared to the standard model. So now, if you run this machine for 1 year, you will reach a limit of order 2, right? So 500 to factor 2, right? So yeah, it depends how much time you want to spend. And also, I would say that maybe those studies, can be improved. I mean, there are various ideas, At the moment, they are looking at the decay of the X into gluon because, there is no background from the decay of the Z. But maybe you can exploit all the decay mode into WW, into BB, which will have, higher rate, whatever, to improve this sensitivity even further, or use some interference or polarization of the decay modes, etc. So I would say this is still preliminary. At the moment, is an opportunity that exists. If you put the number, it seems that it more or less match. It's not 100 years that you need to run. It's few years, and then it's up to the physicists really to come up with, maybe better idea to optimize also. About the up and down, unfortunately, yes, FCC-ee doesn't have sensitivity to the standard model value. Again, high luminosity LHE will be of the order 200 or 400 times the standard model value. So certainly you will improve dramatically those bonds, but there is no hope to really reach the standard model sensitivity.
HH will take that up or not? No.
Not
okay.
that I know of. No.
Okay, thank you.
HH, again, you will pay price of the background. So.
Okay, we still have 2 questions here, please.
Yeah, so the FCC feasibility study seems very impressive and comprehensive, and it seems like sort of the most uncertain part of the puzzle is still just the international funding situation. Are there any updates to that? Because otherwise it seems like the machine is quite well understood.
Yeah, this is something which is, clearly heavily discussed. Even last week there were a meeting with the financial committee of CERN to really understand the financial plan. There is various ideas on the market. For instance, a recent development is this contribution from the EU, right? 3 billion, which will be significant contribution. That's basically what you need. the amount of money that CERN cannot afford. I mean, CERN, within the CERN budget, you could collect something like 10 billion, but you need an additional 5 billion to really secure and go to the 15 billion. So there is this 3 billion from the EU. There is some rumors that rich donors have been identified of the level of 1 to 2 billion. I don't know, this is a well-kept secret, clearly, the name of those people. So, as I say, I mean, there are various models, but there is also various models, within CERN. What do you want to do in terms of staging? I mean, do you really need, for instance, to construct all these 4 interaction points straight away or not, right? And one question, which is actually how much diversity you want to keep at CERN while building FCC. So that will control actually when you want to start. So if you want to start at 2045, you need basically to devote a large fraction of the CERN resources to FCC. If you allow yourself to shift the start by 5 years, then it allows and give more resources to more diverse research program at CERN. So there is all this political discussion that are going on at the moment. Options are there, but
it's clear that we have many more questions than we have time today. On the other hand, it's also clear that this is only the first of 3 talks. There were 2 last questions that I would be prepared to take. I think you had an indication you want. So, sure, please.
I have a question on the chat.
1 second, please. First, inside the house.
Hello, so the question that I wanted to ask has to do with the physics case for the FCC. So I understand that for the LHC, the situation is a bit different because we were working with like a null-lose theorem, like whatever happens, we can guarantee that something comes out of it. And I guess working in particle physics for us is very clear that something will come out of it, but it feels a bit difficult when we talk to someone beyond people who work at the experiments at CERN. And the thing I wanted to ask about is how much effort have we been putting in the case in which there's nothing new? So there's so much that can be gained, for example, from the context of EFT. So lots of papers have these projections of what happens if we have higher energy and we still don't find anything. It still seems like in terms of the EFT limits, we gain a lot from it. But this doesn't, I don't know how much effort has been put into making this sort of thing part of the physics proposal. So even if we don't find anything, that's a less appealing case, but we can still guarantee some sort of
Yes, I mean, there are those guarantees deliverable in the sense that improving the measurement, improving the sensitivity in the measurement of the X coupling, the Z, etc., are guaranteed deliverable. We know that FCC-ee will achieve that, and that will be clearly a progress compared to the knowledge after LHC, right? Now, of course, as you say, it's something which is much more difficult to sell, to the outside community. I mean, as soon as you start talking about EFT, clearly you are talking to experts involved in particle physics, right? And for them, yeah, I mean, people are used to say that the discovery is a new particle, right? But actually, discovering new interaction is also something important. I mean, particle physics is not so much about particles; it's about fundamental laws, it's about interactions, right? And here, FCC has a rich potential, right? And also discovering that nothing exists is a discovery, right? I mean, that came, I mean, special relativity emerged from the knowledge that there were no ether, right? And if you know for sure, if you establish that something doesn't exist, is really an improvement in our understanding of nature, right? So people were expecting to discover new physics at the TV scale. Maybe it doesn't exist, but we need a machine like FCC-ee to be sure to really explore, I mean, a larger range of energy. And the way I see FCC-ee is really like a GPS or a LiDAR, right? I mean, just try to see where new physics could sit, right? And then you will need a new machine to go and explore directly. But when you start a journey, you start putting the address in your GPS. So that will be the result of FCC-ee, right?
We have much more time for 2 other question and answer sessions. We take a last short question from the room, please.
Yes, just to conclude an historical comment. You made this analogy between the discovery of Neptune and the general relativity. I think this could be a bit misleading because Einstein was not developing general relativity to justify the precession of Mercury, even if he was fully aware, I think. But
Right.
if you could comment a bit more on this, because I already saw this slide a couple of times. I think we should be a bit careful.
Yeah, I mean, it's true. What I wanted to say is that, there was this anomalous trajectory and people saw that it could be explained by a new planet, right? That was the hypothesis of Leverrier, this Vulcan planet, and that didn't happen. And the solution came out a few years later with the discovery of general relativity. But you are right that general relativity didn't emerge as, a puzzling measurement, right? It was just the explanation of this anomaly. So first you find out that there is an anomaly, and then later on you try to find the explanation.
Yeah, in this case, maybe the arrow should go in the other direction to be.
Yeah. I mean, the point is that you first need to find out that your current description of nature doesn't agree with experimental facts, right? So that was measurement of Mercury. Mercury doesn't agree with Newton, right? And then you are looking for an explanation.
So I think that the history we will get right at some stage. So we had 175 people online. I see. Now, of course, some people go for lunch. We have at least one question asked via online by Zijin Zhan, and that is about the relation of plans with the decisions of the Chinese government to advance on the Chinese side a collider. I would be prepared to say we will read about this in the European strategy update, but I leave you the last word, and then I make an announcement for tomorrow.
I think in the best of the world, there should be cooperation, right, between the two projects. Maybe it's unlikely indeed to have two very similar machines in the future, but it was clearly stated by Yifang Wang that said that if FCC is approved, then the Chinese are ready to join FCC, right? They are ready to give up on FCC, of CPC and join FCC. Of course, there is the question of the timing, when the decision for FCC will happen compared to the decision for CPC. That's beyond physics, right?
We touched a broad topic, a range of topics. We will, I think, get much more information in the coming 2 days. We meet again tomorrow here, same time, 11 o'clock. And then on Thursday again. Please also recall that on Thursday evening at 6 p.m., I'm not sure whether it's Council Chamber or elsewhere, there is this alumni talk by Carl Jacobs that will also touch on future flagship project at CERN. Okay, thank you very much, and thank you for your attention today.